to our guest is Yasha Gindikin from Minneapolis. He works in William Fine Institute for Theoretical Physics. His subject is Rashba material. He will explain us what it is, although some of us know, but he will still explain it. And the subject belongs to physics of semiconductors, but has overlap with many other things which we do in this institute. So, please.
Thank you. Thank you for the nice introduction. Good afternoon, dear friends. Beyond measure, am I grateful to the organizers of the seminar for the invitation. It's my pleasure to be here. I will talk about pair spin-orbit interaction in Rashba materials and how it affects the electron liquid. It's a pleasure to introduce my collaborators, Alex Kamenev from the University of Minnesota, FTPI, the co-author of the current work, which I'm going to tell you about, and Vladimir Staplikov from Kotelnikov Institute in Moscow, with whom much of the background work was done. So, the spin-orbit interaction is well known from the relativistic quantum mechanics. Usually, it is explained like this: imagine an electron moving in an electrical field. In his own frame of reference, there arises the magnetic field because of the Lorentz transformation, and it's proportional to the electron momentum. And this magnetic field acts on the electron spin, affecting its energy, giving rise to spin precession and all kinds of transport phenomena associated with the spin-orbit interaction. And it's true, but it's only half of the truth. Full truth looks like this. Electron is described by the Dirac equation, which is it lives in 4 bands, and there is a mixing between those bands. And the Dirac equation knows nothing about spin-orbit interaction and, truth be told, about the electron spin. All of this, spin-orbit interaction and spin, arise when you project your 4-band Hamiltonian onto the upper band, electron band, as contrasted to the positron band. So the spin-orbit interaction is an attribute of a simplified one-band, single-band portrayal of electron dynamics in a multi-band system. You can think about this in such terms that external electric field disturbs the motion of electron in all the bands. But due to the band mixing, there arises a response which reflects the dynamics of electron in the lower band, the response in the upper band. And this you describe with your spin-orbit interaction. This logic works very similar, in a similar way for the semiconductors. Here is the band structure of a typical semiconductor like indium arsenide or gallium arsenide described by the Kane model, when you have a conduction band and you have several valence bands that are hybridized with the conduction band. There is a mixing between those bands. And this mixing gives rise to what is called in modern parlor, even if it a bit imprecise, the Berry curvature. But note that the valence band are split by spin, and the reason for the splitting is exactly this very relativistic spin-orbit interaction. Normally, the splitting is large, splitting in the valence band, when the material contains some heavy elements. And those heavy elements create very large nuclear fields, and the splitting is proportional to the z to the 4th. So for heavy elements, this can become large. But then the mixing between the bands can become much stronger than in vacuum, because the gap in the spectrum is very small in vacuum. These are mega electron volts, right? And in semiconductors with strong spin-orbit interaction, these are typically milli electron volts, maybe tens of milli electron volts. So this Berry curvature requires a spin dependent component, which is nothing but the Rashba. By the way, do I have a more civilized way to point to the screen?
Yeah, there is a pointer just under this.
Excuse my blindness. So this is the Rashba spin-orbit interaction, which looks pretty much like to the spin-orbit interaction in vacuum, except for the magnitude of this interaction alpha, which is larger than in vacuum by several orders of magnitude. Typically, we think about 5 or 6 orders of magnitude larger than in vacuum. This constant has the dimension of electron charge times the square of some length, electron times angstrom square. So in vacuum, this scale is the Compton wavelength. So this is the relativistically small interaction. But here in the semiconductor world, the characteristic scale is dozens of angstroms. So it's magnitudes larger than in vacuum. Basically, the interaction works like this. External electrical field acting on an electron couples to its momentum and couples to its spin. And the main question I would like to address in this talk is what is the source of this electrical field? Rashba interaction is produced by any electrical field external to the crystalline lattice, external to the crystalline periodic potential. This can be, for example, in systems with broken inversion symmetries, this can be some kind of built-in electrical field, like when you have a confined, electrostatically confined electron system, like electron gas in a two-dimensional quantum well, this can be the gradient of the confinement potential. Actually, I'm not interested in the systems with broken inversion symmetry. It is not mandatory for the Rashba interaction to arise. In fact, we will deal with inversion symmetric systems. And the question is, what is the source of the field again? If there is no built-in electrical field, okay, no problem. You can have a charge impurity. Its electrical field will give rise to the Rashba interaction. It will lead to the spin Hall effect. This field can be produced by charge interfaces or external gates. There are many ways of creating the electrical field external to the crystalline lattice. Very simple idea that I would like to tell you is that this electric field can equally well come from the electron-electron interaction. Indeed, consider 2 electrons within your crystal. They're interacting via what? The Coulomb law, right? So they produce these Coulomb fields. Each electron feels the electrical field created by the other electron. It couples to its momentum, it couples to its spin, and this gives rise to the two-body spin-orbit interaction.
This Kane model, what is the Kane model? Can you remind us?
It's a classical model of semiconductors like gallium arsenide or indium arsenide. This is an exactly solvable 4-band or including spin 8-band models within which you have the conduction band, 2 bands of heavy holes and light holes degenerate at the center of the brilliant zone, and then very importantly spin split 3rd valence band. That is spin split by the relativistic interaction. And this 8-to-8 model can be solved exactly much similar to the Dirac model. And it gives rise to a very similar low energy expansion.
So I'm familiar with the Luttinger.
No, this is Evan Kane, not Charlie Kane.
No. So that's the right question. He asked me about the old Luttinger model of semiconductors. They were created more or less at the same time. Luttinger model takes into account the warping of the valence bands, and this gives rise to the rotational invariant, no bands, no warping. But contrary to the Latinger Hamiltonian, this one can be solved exactly. So it's a very important example in physics. Then you can add the Latinger-like terms, and you would get a very realistic model which would include the spin-orbit coupling and anisotropy of the effective mass and whatnot. Yes.
So the Kane model is isotropic,
Yes.
but Latinger is
not.
Is not.
And it's rotational invariant.
Please. This coefficient alpha is a pseudoscalar, right?
Yep.
And the formula below looks like a scalar. Yeah, but it's supposed to be pseudoscalar. What control its sign?
Why is it pseudoscalar?
Because it's cross dot product.
But sigma is
Here is sigma also.
It's a vector. Sigma is a vector. P is a vector.
And what
Covector.
sigma
E is a vector. So
axial vector.
yeah. So product of three vectors is a pseudo scalar.
One
Yeah.
of sigma is,
But
sigma is
sigma,
axial
strictly
vector.
speaking, is an axial vector. The
Sigma is a vector. Right?
It's vector of Pauli matrices.
Axial vector. It doesn't change the direction of the.
The textbook says spin is a vector.
Okay. So what controls
What controls the sign of alpha?
It's spin times spin. It's a spin coupling. So if you say sigma is a vector, then you say E dot P, E cross P is a vector.
Is it
It's J times S.
E cross P is obviously
Axial
pseudo vector because it's cross. It requires choice of orientation, right?
But so is sigma.
Well, it's a deep question, but I can give you a simple,
So, what is the sign of-
answer that might not
Question, what is the
satisfy
sign
you.
of alpha?
But the sign of alpha is determined by the relation between those splittings. In case when delta SO is positive, alpha is negative. So the sign normally is opposite to the one in vacuum. While in vacuum we would have positive alpha E times square of the Compton length. Here the sign changes. It might be important for the like various instabilities. But this simple answer relies on the relationship between those splittings. As to the symmetries, I would think a bit about this. We could discuss it later.
This issue about symmetry based on distinction between time reversal and inversion or parity, depends on the dimension. So that's a big distinction.
Yep.
What you have in
For
mind is
sure, it's
time
time
reversal.
reversal
It's
invariant.
time reversal, yes,
Yes,
but
not parity invariant,
not
right?
parity.
Yes, and this is an important thing, but right now I cannot add anything substantial to it. But thank you for bringing my attention.
What is P squared?
How?
What is P squared?
Spherical dipole moment, which is responsible for the band mixing. So, yep,
The dipole transition between the conduction
and valence bands,
and
and the valence bands, three of them.
when all of them
All
has
of
the
them.
same P.
P is the same, but the coefficients in front of P are somewhat different to respect the rotational invariance. So they are very smartly chosen. So the main idea here, is to look at this electrical field that comes from both of interacting electrons. Then this field depends on the distance between them, that is on the positions of both electrons. So this is truly the two-body interaction. And as such, it's very interesting. First of all, it depends on the electron spins that are not predefined and should be determined self-consistently from the equation of motions. It depends on the electron momenta, and the electrons move wherever they want. So this is, generally speaking, a highly anisotropic interaction. Right from the start, it is seen that as compared to usual one-body Rashba interaction, this gives rise to a qualitatively different spin texture of the electron. Imagine you have a two-dimensional gas of electrons, and you apply the external electrical field normal to the plane. It would align the spins of electrons to a familiar chiral texture. So the spins will lie within the plane and form a chiral texture. Now imagine you have this very two-dimensional gas and two electrons interacting with each other. The crucial difference is that the electrical fields, in this case, lie within the plane. These are in-plane fields. And then this interaction tends to orient electron spins perpendicular normal to the plane. No chiral texture, all electrons tend to align the spins in the normal direction, leading to ferromagnetism eventually. But what is most important about this interaction is that it's determined by the electrical field rather than potential. And field grows faster than the potential when you bring two electrons closer together. 1 over r squared versus 1 over r, right? So we can expect that at low enough, small enough distances, this interaction could compete with the Coulomb repulsion of electrons. And when I say compete, I mean one very particular thing, that this interaction can be attractive for a particular spin orientation of electrons. And the mechanism of the attraction is very simple, in fact. Look at this familiar Rashba type dispersion electrons. So Rashba interaction shifts your parabolas, lifting the spin degeneracy to both sides and bringing down the bottom of the conduction band. The stronger, the larger the electrical field is that produces the interaction. Now you take two electrons, you put them closer together, field grows, the bottom of the conduction band goes down, which means that the energy of the electron with a particular spin orientation goes down as well, which means the attraction. And let me start with a bit of heuristics before proceeding with real theory. What would be the consequences of this attraction? Electrons would bind in pairs, and in contrast to this familiar Cooper mechanism, there is no mediator like phonons. Electrons form bound pairs just because they move in particular spin orientations, and the movement can be quite different. Basically, I will concentrate on for a second on a two-body problem, two-electron problem, and I can say that the equation of motions for this two-body problem decouple, so we end up with two quite distinct types of bound electron pairs that correspond to different types of electron motion. Imagine for a second that two electrons are moving as a whole and there is a momentum of the center of mass. Then there arises a spin-orbit interaction that is proportional to the momentum of the center of mass. Think of the finite momentum coupling. So if you look for the energy of this bound electron pair, normally it would grow as the square of this momentum, but because of this pair spin-orbit interaction, at some point a bound electron pair appears, and the binding energy grows with the momentum of the center of mass. And the orbital structure is very interesting. It's anisotropic because there is a referential direction right now. But I will not dwell on this any longer, because I would like to discuss a more interesting, for what comes next, type of electron motion. Electrons can move around the common, rotate around the common barycenter, right? And this rotation also gives rise to the spin-orbit interaction proportional basically to the angular momentum of the electron pair, much like an atom, right? But at this time, this constant can be huge, not relativistically small.
R is the relative
it's a relative
coordinate.
relative coordinate, and in this case for symmetric system, the motion of the center of mass completely decouples. And then there arise
in this electric field, it's a kind of property of material.
no, this is Coulomb electric fields will interact in electrons. It can be screened by the material according to the electric constant.
Don't apply any.
No. Absolutely. Just electrons produce this field. And then they bind in this p-wave pair.
But U is a Coulomb potential? What is
Yeah,
U?
it's a Coulomb potential between them 1 over R, repulsive potential. And this is the attraction created by the spin-orbit interaction, which is 1 over R squared.
How can it compensate for the repulsion? The repulsion, so you said there is a bound state?
Yeah, the repulsion is 1 over r, and this is 1 over r squared.
So it's the bound state at short.
At short distance. It has small pairs, strongly correlated pairs. This, by the way, requires a certain threshold for critical alpha in order for this potential be able to overcome the Coulomb repulsion. But this restriction will be lifted as we consider the many body problem, because basically in the weak coupling case for the superconductivity, you do not need to create pairs and then condense them. You just need to create the correlated state. So the conditions for alpha will be milder for many body gas, but for many body problem. But the main lesson here is that if alpha is large enough, electrons can form a bound pair, rotating bound pair. There is no pairing with zero angular momentum, no S pairing at all, because then no movement, no attraction. Electrons attract each other because they move. Here you see the momentum, and which means the angular momentum too. So the attraction appears for higher order angular channels, L1, L2, and so on.
The spin is parallel, so
And
should it-
spin is normal to the plane. And spin is normal to the plane. So these are triplet states, triplet to body states. So they rotate clockwise, the spin is up, provided alpha is positive. They rotate counterclockwise, the spin is down. Time-reversal-invariant is preserved.
should L be odd then?
How?
Should L be odd because of the Fermi statistics of the two fermions?
Odd. Odd because of the Fermi statistics. Exactly.
It cannot be
So,
two, right?
No, two.
Just
You're
one or
right.
three.
1 or 3 or 5. We consider only with L equal 1 p wave pairing here. Then we could condense those pairs and get superconductivity. But this was like kind of heuristic introduction. Let me start with more substantial stuff. So the main step in solving this problem is to rewrite this spin-orbit interaction instead of the interaction with the electrical field to the interaction with the external potential, right? So think for a second about the one-body Rashba interaction, right? Then the vertex, this is one-body Rashba interaction is produced by some external electrical potential. Then the vertex of interaction with this potential is like this. It contains a normal Coulomb part, which is just electron charge times sigma naught, diagonal on spin. And then it contains the term that describes the spin-orbit interaction. It looks like this. This is alpha, Rashba magnitude, P1 cross P2, cross product of incoming and outgoing momenta, and electron spin. This is again nothing new. This is just the old well-known mode scattering, mode spin-dependent scattering, well-known from the relativistic quantum mechanics. But at this time, this alpha is not relativistically small again. It's huge in materials with giant Rashba effect. Essentially, the only simplest step that we are doing here is that we allow this potential to fluctuate. And when it fluctuates, there is a correlation function of this potential, which is nothing but your Coulomb interaction, which is 4 pi over q square in 3D and 2 pi over q in 2D. And we end up with this interaction Hamiltonian, which is 4 permanent interaction with these very vertices standing here. And what we will be doing next, we will just perform a very simple variational estimate, trying to check if there is an instability in the Cooper channel due to this interaction. So we write this BCS type Hamiltonian, or consider only the pairs with zero total momentum. we can start from three-dimensional systems, but this story is valid for 2D as well. And then we introduce the anomalous expectation values, which for p-wave pairing can be written like this. The important thing is that this expectation value is an odd function of the momentum, because as Danson told us already, only the odd channels are allowed in order for the bound pairs to be formed. Then the BCS energy, the expectation value of the Hamiltonian, is just like this, at least for the short-range interaction, which is just a convenient tool to describe the symmetry of the solution. Of course, this instability will hold for the real Coulomb interaction too. But what is important here, that the instability for the short-range interaction occurs already for infinitesimally small alpha, for very small alpha, because the short-range Coulomb interaction does not contribute to the p-wave pairing because of symmetry. So if this becomes negative, we got an instability in the Hooker channel, and this is exactly what happens. The order parameter that describes this p-wave state is naturally introduced like this in terms of these anomalous averages. And then the BCS energy can be written as a bilinear in momentum form, or in terms of this tensorial order parameter. And the matrix of this form has an asymmetric spectrum. It has both positive and both negative values, which means that for either sign of the spin-orbit interaction, there is an instability in this channel, and the electrons tend to form bound pairs. But the character of the instability and the resulting state depends strongly on the sign of this Rashba coefficient. For negative sign, because this spectrum is asymmetric, there are minus ones, there are ones, but then there is two, right? So this two eigenvalue wins for negative alpha, and this corresponds to the anomalous average proportional to P, isotropic solution. And for the other sign, for positive alpha, the solution becomes anisotropic. So the symmetry is broken spontaneously. But this is just kind of a linear analysis. We should probably come to the self-consistency equation. For this, we can write the usual Minfield-Bogoliubov-Dujan Hamiltonian in terms of this spinor spin times number. And we introduce here the order parameter delta, which again is an odd function of momentum. And the self-consistency equation for this parameter looks like this. This comes from this spin-orbit vertex, this product of momenta. And this self-consistency equation can be solved. And there are two inherently different types of solutions. So for negative alpha, this order parameter is proportional to P. This is very similar to the Balayan-Wertheimer phase, B phase of helium-3. Then we check that this solution indeed satisfies the self-consistency equation. We can estimate the gap and the critical temperature for this solution. But what is funny, that there is also another type of solution which is realized for alpha greater than 0. For alpha greater than 0, there is principally no possibility to get the solution delta proportional to P. But this anisotropic solution really exists, but its critical temperature is different, and the relation between the gap and the critical temperature is altered as well. In this type of solution, which is very similar to the Brinkman-Morel phase, A phase of helium-3, there is no m equal to 0 component. It's T plus or T minus phase. So this is a time-reversal-invariant superconductor. This is exactly what I was explaining in, on the example of two-dimensional systems. You have either clockwise rotating electron pairs with spin up or counterclock rotating electron pairs with spin down, and then we condense them and get this very phase. And this phase also exists in two-dimensional systems. Quite expectedly, there is no phase with delta proportional to p, fully rotational invariant phase in two dimensions, because the system itself is not fully rotational invariant. It's confined to two dimensions. So there is, in two dimensions, there is only this Anderson-Morel phase with critical temperature and all that. But the principal difference from the three-dimensional case is the following. You see, when you have the order parameter like this, it has nodes in three-dimensional. So in three dimensions, this space is a nodal superconductor with nodes at north and south poles. But in two-dimensional systems, there are no nodes, so the state is fully gapped. So this is a kind of microscopic model for a topological time-reversal-invariant superconductor. Then again, how much time do I have realistically?
Half an hour, 20 minutes,
25 minutes.
20 minutes.
Very nice. But then again, the instability in the Cooper channel is not the only instability produced by this pair spin-orbit interaction. We can look at the possibility of the ferromagnetism. As I told you right from the very start, this interaction tends to align the spins, if we think about two-dimensional system, along the normal to the plane. But in three-dimensional system, this would also result to ferromagnetism, but with a spontaneously chosen direction, with spontaneously broken rotational symmetry. So we will do a very simple thing, absolutely. We'll just calculate the exchange energy using those vertices, including the pair spin-orbit interaction. And we will end up with two different phases, one symmetric and one with spontaneous rotational symmetry breaking. The symmetric phase will be paramagnetic. And what is funny about this phase, that its dispersion, well, this is really this Hartree-Fock effective electron dispersion, think of it as an effective electron energy function of momentum, it becomes non-monotonous as a function of momentum. This is because the spin-orbit interaction is proportional to the electron momenta, and if this interaction lowers down the electron energy, there will be a dip in the electron dispersion, and as you increase the magnitude of the spin-orbit interaction, eventually electron will populate the states with higher momenta. So even within this paramagnetic phase, upon increasing the magnitude of the interaction, you could expect the topological Lifshitz transition from the field Fermi sphere to the Fermi shell, provided, of course, other phases in the competition will not win, but they will. If we look at the ferromagnetic phase with the spontaneously chosen direction of magnetization, the situation becomes interesting because, first of all, as you increase alpha, all states with momenta from 0 to some upper Fermi momenta will be occupied, but the dispersion becomes highly anisotropic, and the state will look like a dimpled ellipsoid instead of a sphere. This is also kind of a Lifshitz transition. You change the form of the Fermi surface due to the interaction. But what is funny, as you increase this magnitude even more, this dimple inside the ellipsoid will create a hole in the ellipsoid, and this dimpled ellipsoid will turn into the torus. The axis of the torus is this exactly axis of spontaneous chosen axis of the magnetization. So we again see the topological Lifshitz transition to the toroidal phase. But if we plot the resulting phase diagram into axis, here we have the magnitude of the electron-electron interaction, again, for simplicity's sake, to be short range here. And then here the magnitude of alpha. This story looks like this. Imagine for a second alpha is 0 right now, so we will move along this axis. Normally, at small electron-electron interaction, we have ferromagnetic phase, and we do. It's symmetric. Its symmetry is not broken, and rotational symmetry is not broken too. But then you got your Bloch ferromagnetism. It can be either Bloch or Stoner, depending on the dimension of the system. But here, in two-dimensional systems, there can be no Stoner instability. So it's all the first order transition, so no partial polarization. But in three dimensions, this is rather an onset. There is an onset of this instability, but we neglected the fact here we only investigated here either non-polarized or fully polarized phases. And then we come to the ferromagnetic phase, which at alpha equal to 0 is also spherically symmetric. But as you increase alpha, this sphere becomes deformed. It turns into ellipsoid, it's ferromagnetic phase, and then it turns into torus for large enough alpha. In principle, you can go through all three phases. If you start with not too strong electron-electron interaction, but increase alpha, you go from paramagnetic phase to ellipsoidal ferromagnetic phase, and then to toroidal ferromagnetic phase. There is a caveat here. For short range interaction, the system is unstable in the Cooper channel, and for small alpha, even for small alpha, we already have a superconducting state. While we see that the emergence of these exotic phases requires some finite alpha, right? Ferromagnetic phases. So formally, this solution is within the region where the system already should be superconducting. But what happens in reality? It's an open question. I could speculate a bit if you allow me. The thing is that we are talking about p-wave pairing, right? P-wave pairing is very susceptible to disorder because Anderson theorem does not hold in a disordered system. And most likely that in any realistic system, this superconducting state could be destroyed by this disorder. And so at some finite alpha, we could end up with a normal but ferromagnetic phase. On the other hand, they could coexist, and that would be very funny because in this spin polarized state, obviously only an anisotropic Anderson-Morel phase would be realized. But look what is interesting here. The Fermi surface here is not a sphere, but a torus. And if the Anderson-Morel phase were realized on this Fermi surface, it would have no nodes. It would be even three-dimensional. It would be nodeless. But the coexistence of the superconducting p-wave state with this ferromagnetic phase probably requires further investigation. That's not the end of the story itself, because apart from those instabilities, there are instabilities in the particle Hall channel that would lead to interesting nematic transitions in two-dimensional electron gas stripe-like phases. In one-dimensional systems, that would this interaction would highly affect the latent or liquid state, breaking the charge spin separation and giving rise to an interesting scenario of non-uniform phases with broken translational invariance. But for this, I have no time, so it's probably...
And the pneumatic fluctuations give rise to different kinds of superconductivity from the below?
Yes, but most likely this would give rise to the finite momentum coupling, right?
Yeah.
And this exactly was investigated in a recent paper by Alessandro Principi and his student. which appeared a month ago on PRB, exactly because of this pair spin-orbit interaction, they were able to obtain this superconducting state with finite momentum pairing. Thank you for the question. But that's probably it. Thank you very much for your attention.
Yeah, thank you for finishing well in advance.
Yep.
Okay.
Any
So
questions?
we can discuss.
When the two spins are opposite, then the interaction is repulsive.
It depends on the geometry of the electrical field between the electrons. Think, for example, about the two-dimensional system. And by the way, we have chalk. No, I wouldn't call it chalk. But okay. We'll make let's move it. Consider a two-dimensional system, right? Take two electrons and let this pair move along some direction with the momentum p of the center of mass. They would form, if p is large enough, what is called a convective bound pair. And the spin structure of this convective bound pair is a mixed singlet and triplet T0. So yes, even such spin orientation can give rise to electron pairing, provided you have the right combination of the electrical field and the momentum.
So in the opposite, when the spins are in the same direction instead of the center of mass P, that's a relative.
That's relative. Then they should pair as a triplet, T plus or T minus state, in two dimensions. In one dimension, situation is again quite the opposite to the two-dimensional case because there is a qualitatively different geometry of the electrical fields there.
So in the case of the parallel spins, you mentioned that it would form a pair even without the Fermi surface because alpha is large enough so
Yes,
that
if alpha is large enough, they will form pairs even without the Fermi surface, but the critical magnitude of alpha can be large enough. According to our estimate, it should be of the order of 10 to the third electron time and strength square. We know for sure that for indium arsenide it 10 to the second, but there are materials with larger spin orbit. So in principle, we can find something for this pair to be formed, but it's an open question. I cannot right now point to a particular material and tell the experimentalists to go and find me some bound pair, please. So yes, it will require a critical value of alpha. By the way, for the many body problem with realistic long-range interaction, that would also require a finite value of alpha. It's that for short-range interaction that we see some instability. If the interaction is long-range, then alpha times over AB square should be larger than, roughly speaking, RS. So there is condition for that too, but it's milder. It's milder than for two electron pairs.
Is there any way to measure this external, internal electric field?
Measure?
Just any way to observe it separately?
You are talking about the electric
way to manipulate it?
The electrical field. Well, you can manipulate it by creating different dielectric environments. For example, you can use thin layers of two-dimensional materials that would result in these. Instead of Coulomb, you would get the Keldysh type interaction, logarithmic potential. So yes, there are ways to manipulate the form and the magnitude of the potential by changing the configuration of gates and the dielectric medium and all that. But all these are electrostatic ways of manipulating. Maybe you're asking something more series.
See, in that formula, can we just go to this Hamiltonian initial, the first formula?
Sure.
Formula number one.
This?
Yeah, yeah. So there is a E there, right?
Uh-huh.
So how do I know about E? I can compute it, but is there any way to measure it, detect, test it, or move it around, manipulate it?
Well, manipulating it is possible using these classical electrostatic means, but as to measuring, I cannot think of anything else but classical experiments of creating a hole in the dielectric and putting a test charge. I don't know, no, that's funny. We are talking about electrons. In some sense, this is beyond our reach, the direct measurement of the field of Coulomb interaction. But we do believe that the electrons interact using.
But what is the best experiment? What is the best, maybe Gedanken experiment to test whether there is some this kind of interaction? So maybe not indirect, in some indirect effects.
Well, there are instabilities here. Maybe they require too strong interaction, but even for weak pair spin orbit interactions, there are ways of doing that. Can I draw? We will use this. Think, for example, about the Lagrange liquid, right? So we have a quantum wire. We can perfectly well do any kind of transport experiments on quantum wires. Here we definitely need a gate to break the inversion symmetry because the electrical field parallel to the wire are also parallel to the electron momentum and thus do not contribute to pair spin orbit interaction. But the fields of the image charges, they do contribute to the pair spin orbit interaction. So if we include the interaction due to the image charges and bosonize and solve the problem, we will see that the spin charge separation is broken, and instead of one plasma which transmits charge and spin-on with non-renormalized velocities that doesn't contribute to electrical transport, we have two mixed modes with different velocities that both contribute to transport, and then we can like put the leads here, source and drain, and try to measure the conductance, or to be more precise, admittance, as a function of the frequency. Normally, it would exhibit oscillations on the scale of the transit time through the wire. This is nothing but this optical, like an optical resonators, those resonances. But when you have two modes moving with different velocities, you will have two oscillating patterns with two characteristic frequencies that first can be tuned by applying voltage to the gate, and they should be quite distinct in the transport measurement on the conductance of the wires. In principle, some kind of similar oscillations were really seen in the dynamic conductance of the wires. There was guy from the Utah University, sorry for forgetting his name. He showed me his experiment on the nanotubes with those two periodic oscillations. I cannot just bet that it's due to the pair spin orbit interaction, but in principle, this kind of experiments should be able to test the presence of this interaction and its tunability by external fields, even if the interaction is not strong enough to induce real phase transitions or superconductivity and whatnot.
Okay, so if there is no question, Yakov, thank you very much. And